Now let's look at a more example of a more complicated situation where you've kind of got two sets of events potentially going on. We can talk about probabilities of getting numbers or face cards or whatever, or we can talk about probabilities of colors or suits. So two things going on. Now, kind of working off of this, we get into the very fundamental core rules of probability. And you can see them, well, some will refer to them as one of them is the addition rule. You may see people just talk about it as the OR rule. And that's, in a nutshell, is if two events, what the OR rule tells us, or the addition rule, if two events are mutually exclusive, the probability of either one or the other is just the sum of their individual probabilities. So getting back to the language, what do I mean by mutually exclusive? Mutually exclusive just means that the occurrence of the, well, they're not, actually I want to kind of refiddle with the wording on that because that seems to imply that they're mutually. It's easier to, I think, to describe mutually exclusive. Let me pause for a moment. So mutually exclusive means if one happens, there's no overlap. If one, the occurrence of the event precludes the possibility of the other.
So if one happens, the other one can't happen.
If one happens, the other one can't. There's no kind of overlap between them.
Or,
But there's, yes, there's no, well,
either this
well,
or
not
that.
necessarily. We'll get to that in a minute.
I'm trying to help with the word.
Yeah.
So if you were asking a question, what is the likelihood, what's the probability of you
Trying to
getting
think of another
an
word.
ace or a 3?
Yeah. Well, I think it'll just, I just didn't like, now that I wrote it, I got to think of a more simple way to describe it than the occurrence of the event precludes the possibility of the other. I mean, you just
I'm
see
not sure that is the best way to say it.
that might be the best. It's technical.
That's not bad.
Okay, so anyway, mutually exclusive. If one happened, well, anyway, enough of that. You write this down as the probability of A or B. It's just kind of language. Probability of A or B equals the probability of A plus the probability of B. And that's just the parentheses just mean it's the P is the probability of whatever's in the parentheses. So if I want to look at the probability of an ace or a face card, well, so I need to know what's the probability of an ace. So I look at the aces. There's 4 different outcomes. If I'm sampling, I'm doing my random simple experiment with a deck of cards. There's 4 outcomes that give me an ace. Out of those 52, I'm sampling a card. 4 of them are going to give me an ace. And so the probability of an ace is 4 over 52. There's 12 outcomes that are a face card, a king, queen, or jack. So the probability of a face card is 12 over 52. So the probability of ace, king, queen, jack, or the probability of an ace or a face card is you just add them up. 4 over 52 plus 12 over 52 is 16 over 52, right? Which is 4 over 13 or 0.3077. Right, so that's the probability of an ace or a face card. Now, if two events are not mutually exclusive, the probability of either one, so now let's say that they're not mutually exclusive. It's possible to being one doesn't mean you can't be the other. Maybe you could be both. There's some overlap between them, which is literally what we'll see in a second. So if two events are not mutually exclusive, the probability of either one or the other is the sum of their individual probabilities minus the probability of both occurring. because you have to think about, well, we'll see right here. So let's look at the, well, mathematically we write that down. Something's going up here. As the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. Let's say I want to look at the probability of a heart or a face card. Well, the probability of the face card, we just did that, right? There's 12 outcomes that give me a face card, so the probability of a face card is 12 over 52. The probability of a heart is this column here, right? They're my hearts. So that's 13 over 52. And notice they're not mutually exclusive. There's some overlap. Literally, you could be a heart. Being a heart doesn't mean you can't be a face card. You could be both. So we need to know the probability of a heart and a face card. So if you kind of map them both out, that's these ones right here. These three right here are hearts and face cards. So the probability of being a heart and a face card is 3 over 52. So the formula being they're not mutually exclusive is 12 over 52 plus 13 over 52 minus 3 over 52. So you multiply that all out, we get 25 over 52 minus 3 over 52, or 22 over 52, or 4.231. That's the probability of a heart or a face card. Kind of the key. What?
Oh, I don't think this formula was in the book.
Yeah, I mean.
No, okay,
This part of it was not.
good. This
It
is
was,
good.
makes more sense.
Kind
It
of.
makes, no, this is
No,
good, because then it
push
makes
it
a
a
little
little
more
more.
sense. Yeah, I know, it's good.
But it just was, yeah, it wasn't. I was sitting here going, did I sleep through that part of it?
No,
I'll agree with you.
it's. I
No, it
mean,
makes sense, because then
It's
you're still
possible.
asking or, but there are times when things aren't mutually exclusive.
which is yes.
Thank you for sharing.
My pleasure.
Good way to explain.
I'm someone that would have done a little, if I was writing the book, but that's why we have TEDs to write these books. I'd have probably gone a little more into probability.
You probably would have put permutation in with probability.
I
Yeah.
probably would have, and then no one would ever buy my book because they'd say, what is this stuff?
Depends what you title it. If it's, you had gambling in the title, you'd
Sell a
be
lot.
bestseller, yeah.
So where were we? So back to it, yes. This is important because in a way, you can think about it, if they're mutually, if in the end, this is really the more general rule. Because if they are mutually exclusive, what's the probability of A and B if they're mutually exclusive? Is 0, so that just drops out. This is really, the other is a special case. The mutually exclusive rule is just a special case of the general formula where it drops out. You haven't done the AND rule yet, or multiplication, or the AND rule. And that gets at if two events are independent, then the probability of both events occurring is equal to the product of those individual probabilities. Okay? And what I mean by independent is that the occurrence of one event does not change the probability of the other event happening. So if one thing happens, the other, that tells you nothing. It doesn't make any, it doesn't change the probability of the other. So for example, you can think of it as they're uncorrelated. Is a way that it's like shoe size, and knowing shoe size might be independent from whatever. So independent, again, the occurrence of one event does not change the probability of the other. That they're just kind of unrelated to each other in that way. Mathematically, we write that as the probability of A and B is the probability of A times the probability of B. Question? Think of A and B as just generic terms. The probability of something, I could just say the probability of something and the probability of something else.
Right.
It's not the same A's and B's.
It might be the same, actually.
Well, it could be, but it's just
Got it.
a way of saying something and something else.
Placeholders for events.
Placeholders for events. So let's say I want to look at the probability of being red and a face card. So the probability of being red is, well, we know there's 13 hearts, 13 diamonds, that's 26 out of 52. The probability of being a red card is 26 out of 52. The probability of being a face card, once more, is 12 over 52. We've done that. They're independent of each other because if I think about it, if I'm a face card, what's my probability of being red? Well, it's still half of the cards, half of the face cards are red. And being a face card has not, so face card and suit or suit color are completely unrelated to each other. The probability of one doesn't change given the other. So the probability of a face card we saw is 12 over 52. Then we need to know the, oops, gosh, my kid's going. So the probability of the king, yes.
So that 6 over 52 is the same of multiplying out the 12 times.
Oh, my little slide didn't work here.
That should be all 4 rows colored in, right?
Yeah, something got lost.
Should we 12 that?
Or all 4 columns.
Well, don't worry. See my animation. Somehow my animation got out of order. Whoa, there we go. Okay, so don't worry. We'll ignore the shading in. But these are the ones that are the. I still wanted to have the shading, but I lost the shading somewhere. So right here are the face cards and red
So that's
that are red. So these are the ones we're interested in. So to get that probability, it's 26 over 52 times 12 over 52, which goes to half times 3/13, which is 3 over 26, which is 0.1154.
So if we looked at this, though, we could just say 6 over 52.
You could just look at that and instantly recognize, oh, it's 6 over 52, of
So
course.
it's not, okay, it is the same thing, because that's, okay. So
6 over 52 is 13 over 26. Yeah. But sometimes 6 over 52 is not quite.
You're
It's
not
not
gonna be
quite
able to
that
see it
easy.
that way.
When we get into later towards the end of the semester, chi-square, we'll get into probabilities and then this concept of independent a lot more and kind of what happens when they're not independent. That the probability of one does change based on the occurrence of the other. Are you more likely to vote for a Democrat or Republican if you're male or female, or black or Hispanic or white, or Baptist versus Catholic versus whatever? There's all sorts of things that. See, I had to go back to politics because they're such easily compartmentalized boxes.
Ripple electricity goes through the room.
But that's all we're going to say about that. We're not going to go there. But
where's the chocolate?
okay, so enough of this. So these are these concepts of probability that we'll revisit. The key ones again is this idea that you can have these distributions. That we've talked about distributions in terms of kind of how spread out all the kids are who take the SAT, or all the how many hours are people working, and incomes of teachers and stuff. But we can do the same concept. Instead of talking about the proportion that are paid more or paid less or study more or work less or whatever, we can talk about distributions in terms of probabilities. And we're going to do that the rest of the semester and all next semester too, is talk about distributions as ways of illustrating, or not even just illustrating, reflecting or encompassing, being probabilities. So we can go back to our